fractals is a construct of mathematics, and it's a recursive algorithm. Through a recursive algorithm, you could generate a very chaotic structure. These structures generally can be used to design trees, leaves, and other things. It can give beautiful structures. There is a beauty in this mathematics, what you see in fractals. Now, this is the background to this image. This slide is a fractal. As you see that it gives you an effect of trees or galaxies, but this is a mathematically constructed shape. It looks like motifs or decorations, but these are connected with mathematics. So what are fractals? Iterative patterns, infinitely complex, appears in nature like leaves, snowflakes, DNA structures. They all have fractal in nature. For instance, here I've given you an example of a cauliflower. Now, what is a fractal? Say, for instance, you see this. This is not a total cauliflower, but a slice of the cauliflower. Now, what you see here is the slice looks like the total cauliflower. Okay. And if I slice one of the branches of this cauliflower, this itself will look like the total cauliflower. Each of these branches will look like a self-similarity which is there. Again, further, if I divide this, I will again have a self-similarity. Similarly, you see here that there is, if I chop this ice crystals at different location, I will still have a similarity to the total. In fact, here we will see in this formation of a leaf, it's a set of self-similar things. We will see how with just simple rectangles, iteratively placing, you can generate this complex leaf, for instance. And this is basically using self-similarity, which is there. The total leaf is similar to this one of the branches. One of these branches similar to the smaller branch. So basically, you have a parent-child relationship, and all of them having the same structure. For instance, here it is a little more complex, but it gives you a beautiful effect. It's again a fractal structure. This structure can be designed. It looks like a ghost ship or the ships on the Pirates of Caribbean, and and this is entirely generated with mathematical functions. Here you have a structure which is an extremely complicated, complex structure, but then this is again generated through mathematics, and it's fractal in nature, or it's a 3D fractal what you see here. Now, what is a non-fractal? Supposing I take a circle and I keep expanding the circle, taking a portion of the circle, I will never return back to the circle. But if I have a jagged edge, like for instance, the coastline of a country, and if I keep zooming, you will see that it will, at some time, there will be a self-similarity of repeatability which comes in. The coastline will look again similar to the original coastline which is there. So there is a self-similarity in the thing that it may repeat at every iteration, but it may repeat after a cycle of iteration. And now that depends on how you treat the fractal. So that is there. Say for instance, here if I plot a set of globules or spheres, each of 1 centimeter in size, and place it randomly, I won't call this a fractal because they are of the same size. If I chop a portion also, it will not look, and expand it, it will not look the same. But in contrast to what you see here, I have a size distribution, and with a size distribution, I've got multiple size globules or spheres kept. And so if I keep zooming into it, for instance, this is the largest sphere. If I zoom into it, this will take the place of this. These smaller ones will take the place of these, and the black one, which is the smallest, will take the place of the next bigger one. So this structure, which is there, is a fractal structure. What you see is that the size factor has been halved. Here it is a 2 centimeter diameter sphere. let's say 1 centimeter diameter sphere, half centimeter diameter sphere, 1/4 centimeter, and so on and so forth. You can generate uh, spheres of smaller and smaller dimension, and this sort of a structure gives you a fractal structure, and this is what how nature is. If I check pebbles or any other thing, they are of this kind. You don't have a specific size, but you have a distribution of size. So what you see here is a distribution of different sizes, which is there. So the main part of fractals is that it is self-similar. So we have seen how this land, if I keep zooming in, it will have. For instance, here this is called a Sierpinski triangle. If I take a portion of this triangle and expand it, I will get the total triangle. Even further, if I cut a portion and as I further expand it, I'll keep on getting the similar triangle. So basically, this is drawn iteratively. For instance, where do I use fractals in nature? We see blood vessels in the retina. Now, what is important in the retina is that the retina has to supply blood to the whole of the retina, but it should not, it should occupy least area so that the cones and rectangles, which are actually light sensitive, can occupy, because these veins will opaque the regions which is there. So you need to cover the retina maximum with detectors, that is that detect light. But then these detectors have to be supplied with fuel, that is blood or oxygen. Oxygen passes through this blood. So basically, this should spread across the retina, but should be practically of zero dimension. This is possible through a fractal. In contrast to this, what you have is the ventricles in a lung, where basically you would like to have maximum area over which this exchange of oxygen can take place. So when the lungs blows in air, or you breathe in air into the lungs, these air can go into the smaller ventricles and the exchange of oxygen can take place. This exchange can take place, which you require an infinite area over a finite volume. Your lungs having a finite volume, but what you get through a fractal, you get practically an infinite area, the surface contact area through which the exchange can take place. And this is why the lungs, the ventricles in the lungs has been created in the fractal, like a fractal domain. Even in construction, if I want to build a beam or anything, I don't want the beam to be heavy, but as strong as the original full beam. So basically, the beams are sometimes designed as fractals. You will see in airport most of these beams, but you see these large beams that is covering large areas between two pillars are of a fractal nature, and it provides you the strength, but at the same time it is light. So now let us see how a fractal is made. So fractal, see, what we assume is a parent-child mode, where there is a parent and a child is produced. Sometimes the parent and child remain, or sometimes it is the parents are replaced by the child. In this case, the parent will remain as well as the child will remain. So what you have is a parent, and you generate children. So here you see this is the original parent, which is one. It produces two children. These two produce each one two children. So it is four sub children. And then you have got eight sub children, and then 16, so on and so forth. The calculation goes in this manner. Now this is production of children, which is there that you produce other objects on a scaled down version of it, and the number of objects can be 2, 3, 4. In this case, it is 2. The third part is an algorithm or a method of placing these objects in the scene. For instance, I place the parent here, and what I say is that I mark the origin of the uh, of the children to be the head of the parent. सर के ऊपर बैठाना जो कह रहे हैं ना, वो this is basically sitting on the head. So, and I will move it by plus 45 degrees and minus 45 degrees. Now, why 45 degrees? I could take any angle theta. We will see that if we take different angles, I will have different structures. Now, to begin with, let us take some angle theta plus minus same angle theta. So, I have got the two children which have been placed. Now, the children become the parents. So, iteratively, now I'll place two children, their children, on their head and their children on their head. If you continue this structure will be similar to the blood vessels in the retina, which we have encountered earlier. So this is the type of structure. You will see that it occupies less amount of surface area and it spreads over a larger volume where it can transmit the blood or oxygen or food to the different sensitive cells, light sensitive cells of the retina. So, so geometric modeling, there is a mesh, hierarchical, curvature, and procedural. There is a particle system and a fractal. Now, what you see that what I talked about the fractal nature was it's a recursive algorithm. If I tell you to make a fractal, maybe in the assignment, you will see that you will apply a recursive algorithm. Now, as you know, recursive algorithms are extremely costly, and since it's going to take a lot of time, it is not possible to generate fractals in real time. So what is done is that you generate the vertices or the vertices related to the fractals beforehand and feed it as a data to the image. So it's a reading of data, which is maybe most of the time the fractal is complex, is faster than actually computing the fractal position. So the data of the vertices is read and then we use a simple algorithm to just plot it or display it. So here what you see is, in this case, what you have, the parents are replaced by children. For instance, here this is a square. Assume it's not showing well because this is a square. Assume this to be a square. Now we assume the square to have 5 children. What are the 5 children? 5 children will be of size 1/3 of the square. Not half of the square, but 1/3 of the square. Right? The size of the square will reduce by 1/3. And we'll replace the parents by 5 children. Okay, here you see that there are 5 children. The scaling factor is 3. Okay, reduced by 3, and the number of children is 5. So you will place the 5 like 4 in 4 corners and 1 in the center. So this is how this will be formed, and again each of these children would be then replaced by their children, where you will see that the structure like this, and then further division if we take, we get this structure and so on and so forth. So here parent replaces the child, right? So here I have got the image where the parent is replacing the child. Now here I've done the calculation. If you want, you can make a calculation, since at each iteration I generate, say 0th iteration is my initial parent. In first iteration I get 5. In the second iteration I will get the number of squares will be 25, and in the next iteration will be 25 times 5, that is 125, and so on and so forth. It continues. Okay, this is the number of squares increasing. Now the length factor, length scale. So length scale, you see that it is 3 to the power minus n. Now for n is equal to 0, the initial stage, it is 1, that is the scale, that is the side of of the parent square. Okay. Then 3, n is equal to 1, it is 1 upon 3. Then again it is 1 upon 9. Then 1 upon 27. And it continues like that, and you have the area. Now, supposing I would like to find out what is the total area of the squares used by these thing after nth iteration, the area would be nothing else but the length of the square, that is L square n, that is the area of the one square. Now, how many squares you have? Got n squares, and so by multiplying that, I will have a term like this: 5 by 9 to the power n. Now, as you see that n tending towards infinity, since this is less than 1, you will see that this will converge. That means basically the area will, for n tending towards infinity, right? So this will since it's less than 1, it is going to converge to 0. So basically the total area is getting reduced in this case. And I will define dimension as a term of this kind. Please remember L, I've got, this is a dimension. Dimension is defined as log of the total of the number nn. That is, after nth iteration, what will be the number of children divided by log of the length scale. Okay, the length scale, as we saw for that thing, that length scale reduced by 1 by 3. So log of 1 by 3, and this will come to effectively a log 3 pi, which is given here in this manner. So this is called a dimension to the fractal. And as you see, this dimension is not an integer, but it's a fractional dimension. And because of this fractional dimension, sometimes this fractal is called a fractal or a fractional dimension. Okay, so this is important to know what is a fractional dimension. Dimension. So similarly, I can have a triangle and I can keep fitting further triangles, and I can continue this and define its dimensions. So here I have about the coastline problem. We have seen this is one thing. Create fractal geometry created by Mandelbrot. It's self-similar, depends on scaling, leads to an idea of fractional dimension. Fractals are graphical fractal objects. So here what you see here is I have a straight line. This straight line, I replace it, the parent is replaced by 1/3 line. Now, how many 1/3? We will say that we will choose 4 1/3. Now, what is this 4 1/3? This 1 1/3, other 1/3, this is the other 1/3, this is the other 1/3. Now, each of these 1/3 is going to have 1/3 which is there. So it has to free 1/3 in each case. And you will see that you will replace it further by this fold, what you see here. This replacement is done. Okay, so here I have got the same thing, same property can be defined in a 3-dimensional volume. So if I have a cube, I divide the cube into totally, if I take 3 by 3, this is 9, 9 and 9. So this will turn out to be 27 cubes. Now I will say that I don't have 27 children, but I will say that I will have each surface. For instance, this surface will have 1, 2. Say for instance, it will not have the central piece, and say it will have the side piece of this. So similarly, this will not have the central piece and it will have all the sides. So similarly for other things, and here similar for the top view, it will not have the central piece and will not have the bottom piece. So finally, what you get is a fractal structure which is of the second order, which now you can keep increasing the order and create a complicated file, and you will see that this turns out to be something like this. Okay, similarly, I've got Scotch and Sierpinski gasket. It would be nice if you can sort of form these examples. So here you see that the dimension of the pyramid is defined as log 4 upon log 2. Here the dimension of the square that we have constructed is equal to log 20 upon log 3, because the size of the square has been reduced by 3 times and there are 20 such squares which have been placed. So if you see here, you will have 8 squares plus 8 square and 4 pillars. So 8 plus 8, 16, 16 plus 4 is 20. So therefore you have got 20 such cubes which are produced. So it straight away defines the cube. Then what you could do is that I could generate a randomized situation. Say for instance, I have got P and Q. I can take the center part of P and Q and jack it up by some random number. Here some in the normal direction, I push this point by some 10% of the length PQ. I could take 10% or I could take some fixed amount. Now, what you have is two children. That is, one children is P, whatever this point here, and another from this point to Q. Okay, now these two children, again, I'll take the centers of these and then push them out. So effectively, what I have generated is that I'll generate these things. I'll generate some sort of an odd shape or like a mountain which is there. Now please note that I've taken the center, but it is possible that instead of the center, I can choose a point randomly along PQ. It does not matter, and the method will be the same. The children will be of different sizes that occur. Okay, so so here you have got the volume example where you have the dimension which is given in these two conditions that you see here. So here you have the randomization through which we get the polynomial. Now I come to a different property. This was geometrically trying to represent a fractal. I could represent a fractal through an equation. Now to represent an equation in two dimension and in a single equation, it is difficult. So what I can do is that I will choose the x-axis as a real axis and the y-axis as an imaginary axis. You must have used this while studying electronics, any subject of electronics or controls or anything that you have use this where j axis, the y axis is j axis, and this is the real axis which is there. So if I keep designing this model set, if I design this model, I'll get a structure, such beautiful structure which is shown here. So here you see the Mandelbrot set which is generated, and this, let me show you, these are the Mandelbrot sets, just to show you in the beginning how it looks like. So these are further sets of Mandelbrot sets, and this is the different, let me see if I have the equation of the Mandelbrot set. Let's not bother about the equation. So here you see how this Mandelbrot set keeps changing. Now Mandelbrot set is defined as simple z zk plus 1 is equal to zk square plus c. z square plus c. So here you see that because of this offset c, you will get different regions of the space and you will generate such beautiful structure. For each c value, I can choose a particular structure and keep following the structure to get this image. So here is another see here the conversion of one fractal into the other. This is again another conversion of the fractals. Well, these are two I'm not being able to play them. These are two videos of the online and here is the three fractal. You see that if I change the angle, this is at an angle of 45 degrees. This is obviously angle more than 120. And this is 90 degrees. This is for other angles. So you get different fractal structures in this problem. Okay, I'll